So today I want to talk about LADS OPC UA, the common language for lab and analytical devices, a brand new standard. It was published December last year, so it's just 4 or 5 months of the market. And I love what I see in your background, Jochen, enhance your data. I think that's also very important. That's what we want to talk about. And first of all, give me a very short feedback. I don't see you, but has anybody ever heard about OPC UA or even LADS or something like CLA2? So about communication networks for laboratory and analytical devices? There's, yeah, one. Okay. Sorry, I'm an engineer. Today it will be technical, but however, I really want to make it as simple as possible to use. So I know that you're great in research data, analytical data, scientific data. So there's a great match. And this is so there's a standard. Well, that's the takeaway message. Oh, there's a standard, and it's an OPC standard. I will in a minute explaining what is OPC. It's one of many OPC standards, and it's released, and as mentioned, just December last year. So don't expect that now all device, there are a lot of device vendors interested, we will go into that, and also software developers, but don't expect that all the instruments will have this integrated tomorrow. You know, this is a very, it's a long-term initiative, and we are doing a lot of bringing it to the market, and there are already several device vendors and also software providers for our domain working on that, but this will take some time for sure. The takeaway message for you is, wow, there is a standard. And now let's a little bit, as an introduction, talk about the current situation you face every day in your lab. There are tons of highly specialized devices are sitting on the benches in your lab from very different device manufacturers. I'm always surprised when I go in a lab or also make the hackathons or work with the others interested in that there are device types I've never heard of. Not just the device vendors, but also device types and vendors I've never heard of. So it's a very heterogeneous environment, and you are aware of that. Most of those devices, you're as a scientist, as a researcher, you're interested in the data coming out of the devices, analytical data, whatever. And typically it comes in vendor-specific standards, or it comes as CSV or PDF or whatever. And there are a few standardization initiatives around for data formats. I just named 2 of them. It's Animal, this XML-based description language for techniques and the results. Maybe some of you are aware of that. And there's the, at least for life sciences, there's the Allotrope Foundation, which also defined and specified formats for data for scientific data. I'm sure there are more around, but of course there's some shimmering on the horizon because there are some standards. And when we talk about I have all those different devices sitting in the bench, how do you get the data out of these devices? So hopefully in a standardized format, I think that's still ages until this is solved. This is really something which is not solved today. So device connectivity, and what we wanted to do with our standard is really to improve this situation, to make a standard which suits to all those different things. And for number 1, fosters integration in the lab so that you really can interconnect all those laboratory and analytical devices in the lab, talking the same language, and that we also cover this very heterogeneous environment of very different lab device types and vendors. And this is a quite challenging task, and good that 30 years ago, my research work was about this topic. And you know him, I think most of you know Joe Richard, the former Vice President of Analytical Science, BASF. He always states, no standards, no digital transformation of the lab. So we need more standardization in terms of communication standards. So data in motion, bringing the data from A to B, live data, and data exchange, data standards, so that the data formats are right for the data in rest when it sits in a database or in some whatever file to whatever data format or in the cloud. So data in motion, live data, that's more when you have an online exchange with the instruments, controlling it, starting it and fetching the data from it, and then of course data in rest. And today we talk about what is LADS OPC UA, but how does this fit together with fair data? Because of course, this when we took a look at what we're trying to achieve with all the standardization for formats and for device connectivity is much better data integrity, much better reproducibility of experiments, more efficiently through automation, lower cost to result. Maybe that's not in the academia, but maybe in industry. And of course, fair data. And that is what you are very aware of, because this is I think, to my understanding, the major topic of your initiative. And I already used these terms, data in motion for the online data, for the real-time data, which goes through a network live when you connect to your instruments, want to control them, I want to monitor them and fetch the data, and your data formats. How do you combine those different kinds of data? So how is there a common language for this different kind of data that you really have data integrity between them? And typically what is great when we talk about fair data, whether it's in data formats or device connectivity, or for example, ontologies and taxonomies, which help to clearly define the semantics and the meaning of what we are talking about, and not just this is just a number, but maybe this is the temperature in a column of an HPLC or whatever, or this is the peak of an HPLC chromatogram. So this is really would be very helpful if we can bring these worlds together, because then we would have a great foundation for digital transformation. So this is once again, so what we want to achieve really in the laboratory analytical domain is the data integrity from instrument via your desktop all the ways to the cloud for enterprise and academia. And I stole this image from the Allotrope Foundation, I think, because it nicely depicts what we want to achieve and what we are talking about. Questions so far, or simply continue? So I continue. So before telling you the story how we can achieve data integrity in what the data of a network of an instrument has in common with the data you have, your experimental data or scientific data, let me explain what LADS OPC UA is about. So what's this companion specification? This is the standard which now hopefully finds its way into all the laboratories. So when we started, this is well, LADS means Laboratory Analytical Device Standard. Obviously, it's very focused on the device itself, on the instrument. How can you monitor it, control it, get the data of it? So we started with defining use cases. So what we try to achieve, what's in the scope of our standard. And of course, it always starts when we talk about devices, instruments, it's with the monitoring. So you want to know what's going on your device, which is the state. How long, which experiment is it running right now, for which procedure protocol, how long does it take until I can fetch the data, and things like that. What is going on or what is going wrong? So this is number one. So remote monitoring. Then you need this for basic operation over the network. Next is remote control. Maybe if you have a workflow and you really want to automate the workflow somehow in your lab, you want to be, okay, now let's run this experiment according to this procedure or protocol on the first device, and then invoke it on the next device, things like that. So you have to control all those devices. You need remote control. So this is the first box, and we call it basic operation. So this is really the foundation for everything you want to do. And the next level is something we call it program management and orchestration. Of course, typically when you make an analytical run or whatever experiment, you have a workflow with different steps. You have to do sample preparation, and you do something, and maybe then you have the analyzer, and maybe it's also multi-stage analytics you have. So in each of the devices, or a lot of the devices you're utilizing, they have built-in programs, program templates. Maybe you defined them with some cool software provided by the device vendor, define some chromatography procedure, whatever. It sits there. And of course, it would be great for automation and integration if for each and every instrument you have the same interface, the same language, how to look, oh, I have this procedures programs available on the device, and then oh, the device right now, it's sitting there idle, it's prepared for the next run. Please start this analytical run now for this samples, with this parameters, utilizing this procedure. And then in the end, hopefully this analytical run went nicely. On somewhere are the devices stored, and it would be great to know where the devices are stored so that it's standardized and how to fetch them from a device. Vendor independent of which vendor it made it, things like that. So this is the second box. It's about program management and results management, and we call it simply orchestration. And then the last but not least, it's more about, maybe that's more for industry. It should also be important for academia. It's all things service and asset management. So where are my devices? Can they be utilized? Are they idle? Have they to undergo any service or calibration or validation or cleaning? All that stuff, that's service and asset management. These are the use cases that we addressed, and we added as a, let's say, stretch goal, another use cases. This will be for the next work. It's also how to enable lab devices that they can interact with collaborative robots. And this is well, a trend you see everywhere, and that's cool. And I will cover this in a minute. That we utilize as foundation an industrial standard. OPC UA is the most established, the widest established industrial communication standard. And of course, there are already things defined for robotics, and we can utilize those things and apply them to laboratories. Okay, these are the use cases. So in the end, what we want to achieve, you have this lab with all those different devices sitting in a bench or somewhere, and there are all the applications that are waiting for the data in a structured in a way, like SCADA for monitoring, LIMS, ELN. I think this is something very important for you. Workflow management, analytical data systems, maybe things like asset management, and all this has to be integrated and interconnected. So we need such a common language, and it should support those use cases that we just defined, that I just introduced to you. And it would be cool for a future application that we can use this one language all the way from the small device into cloud-based application without losing data integrity. I think that's the key point. It should be not that because you have to deal with timestamps or things like that. This should be and the semantics, what is this just a number, 37.3, or is it a temperature in degrees Celsius? All this has to be clear from the device, from the bench, all the way to cloud. That's what we try to achieve. And well, if you try to define such a standard as such a common language, would be crazy if you start from scratch. Of course, you should look what's already there, what's already proven, for example, also in other industries. And can you utilize a big foundation where you start your work on, and hopefully maybe this foundation, even when we talk about, let's say, quality control in pharmaceutical application or chemical applications, is it something maybe that's already established in manufacturing, but it can be utilized in the QC lab next to the manufacture of the production? And this is exactly why we choose OPC UA. OPC UA is the proven most widespread industrial interoperability standard. It's utilized so everywhere in process industries, all the way to pharmaceutical, in discrete manufacturing. So think about automotive, but also think about all the pharmaceutical companies. So, and it's proven, it's secure, but well, today this is a must-have because it's so widespread. It's widely platform independent. You can really put it in a small microcontroller. It works into the cloud. And that's very important for our topic, for enhancing the data, is it has very great information modeling capabilities. So it's not just about here's a row of raw data. It's really it has object-oriented modeling capabilities with all the things that you can think about. And this is key for plug and play and for data integrity. It has very strong semantics. So the data comes with a lot of metadata and semantics. It's a true and open standard. It's an IEC standard. That's very important for engineers. And well, I don't know about how it's in your analytical academia domain in the chemical analytics, but to really have a, let's say, a smooth way from the bench to the cloud. It's, at least in the industry, it's a requirement which is stressed more and more. And another cool thing, it provides already, if you utilize an established standard, it provides a lot of building blocks. There are 99 whatever different standards, OPC UA based standards with everything you can think of, and one of them even deals with referencing external semantic definitions, so referencing data to taxonomies and ontologies. So there's a lot of stuff which is already there. So that's the reason why we choose this. We have chosen this, and okay, I highlighted this already. What I think is important for when we talk about enhancing your data. And it looks like this. So we have the foundation. This is all the OPC standards, which is the industrial interoperability standard. And then this is let's think of it as a very lingua franca, a very common language which serves a lot of things, of course. And then you have, you need more specified, domain-specific languages with domain-specific semantics and pragmatics. And there are tons of them. And we made, so for example, for robotics, indoor positioning, or for asset management, but we made the one for laboratory analytical devices. This is what LADS is. It's the OPC UA-based language for laboratory analytical devices, and it interoperates smoothly with all those other bits and pieces. So you can quite easily, and there's a nice video, I can share the link on YouTube, how to simply, if you add those robotic stuff to a laboratory analytical devices, out of sudden, a cobot could find its way through the lab and knows where to put the sample or a plate or whatever, all that stuff. So this is it's like, think of it like a huge big box of very nice bits and pieces you can put together, and they operate with each other. And I already showed this. This is our specification, and those domain-specific definitions specification, they are called companion specification. They're built on OPC UA and then define some more things for special industries or domains or whatever. And there are hundreds of them. And in the next slides, one of the next slides, I'll show you that they also can nicely integrate and interact with data addressed, so like scientific data in whatever format. Okay, when we made this I will go through this very fast. So when we made the standard, one of the biggest challenges is all the heterogeneity in our domain, and we just invented something like device type agnostic modeling. So we did not put the device types into the standard because there are way too many. We have found a better level of abstraction. And of course, we said from the beginning, it's very important and crucial that all the data we have in the network, so for the instrument data, has already very clear semantics and metadata. So because this is key for fair data. So, and just to give you, and now the introduction how this works. These are two lab devices. It's a centrifuge, and this is an HPLC. And now I'm talking just about the communication view. So if you utilize LADS OPC UA and take a OPC UA browser tool and connect to the device, and what can I find in there? It looks very techy, very engineering. So you see there's the device with its nameplate, who made it, blah, blah, blah. And if you drill down a little bit, okay, which components is built of? Maybe that's for servicing and calibration. But for you as an end user, it's more the functional stuff. What can I do with the device? And you see that's with all its very different devices types, so centrifuge and HPLC, it pretty much looks the same due to the standard, so that software can find its way around. And then I won't go into detail, but for example, when you go down to the function set, you will find really what this thing can do. Temperature control and rotation for a centrifuge and all the other stuff for all the different modules you find for the HPLC. And I'd already talked about this program manager for orchestration. Where can I find all the program and recipe templates? Where can I invoke the current run or the next run? And where find a result data? That's down in this magenta box. This is where you will find all the result data, stuff like this. So this is the point of view from communication, connecting live with the device. maybe that's not of the major interest for you. It's more for you, it's more about the results. I will come to that in a minute. Let's take a closer look at the HPLC. Here's an HPLC. And now we're not talking about communication, but about machine-readable semantic definitions, what an HPLC is about. And I utilized an ontology by Allotrope. It's for the life science, their life science domain. There are other ontologies around, and this is it's utilizes semantic web technologies to describe our domain, this Allotrope ontology. And you will find when you look at this ontology, what it describes. For example, you will find something about what is a liquid chromatograph, and it's machine readable. What is a reservoir bottle? What is a pump? What is an injector? What is the chromatography column? What's a detector? All that stuff. There are semantic, machine-readable definitions for that stuff. I think that's the takeaway message. And not only for the equipment, maybe this is not any major interest, but also what is chromatography as process? So it's a process description. And also think, what is a result? What is a chromatogram? What is a peak? All that stuff. So you have the definitions and based on ontologies for all that stuff. Machine readable as standard. And of course, now I replace this real HPLC through its network presentation as we provided. And you will see our network presentation over OPC UA, LADS OPC UA, has the same bits and pieces. It represents the same data as live data. And of course, we could, by utilizing those ontologies, we could simply describe in a very fair data way what information is there accessible on the network live. So you can know that you're dealing with the temperature controller of the chromatography of the columns, things like that. And there's a technology we don't have to invent; it's already there to exactly achieve that. And now you see how it works. There's the device on the left-hand side. In the middle, there's the OPC UA representation for the real-time data. I just opened here from the detector the sensor value, and then you can link all this data to semantic definitions. So those dictionaries, and there are tons of different dictionaries, and then you have a clearly defined, fair knowledge, machine readable about all the data and its meaning and its semantics, on which you find in the device on the network. And now it's a good question. This sounds good, but does this work, for example, also for my result data? So let's take another look at the device and at this HPLC, and it just performed an analytical run, an HPLC run. And somewhere in this tree, you will find the result of this run. So there was a run, isocratic solvent, whatever, with some name, and there's the timestamp when it did run, and there's somewhere the results are in different formats. They are stored here somewhere in a structure, and you can access the structure. You can download the files from there, and in different formats, animal or allotrope, or maybe something vendor specific. You have all the metadata, like which program template or recipe was used, who did it, when, from where to when, which samples were injected into this run, all the, maybe there's a supervisory ID for this run in my LIMS system, things like that. All this data comes together, and they're still looking at the OPC stuff, and maybe this HPLC already did, for each sample or for each run, did already do some pre-processing, finding the peaks. And then maybe you look at this here, you find the chromatogram. So there's already a data structure for the chromatogram. There are, maybe here it listed for this sample with this sample ID, it already listed all the peaks and the area and the end and the height and start and baseline, stuff like that. Yeah, well, it's nice, but how should a machine-based system, a computer system, automatically understand that what we call peak and what we call chromatogram is in fact a peak, a chromatogram? This is where those ontologies come into place, because already in the network, we can link all those things. Here, this is the peak number 1, and we can link it to the definition of a peak. And then for a system, it's clear it's not something that is called peak, it's the peak of a chromatogram. And this is fair data. You have all those, and it's not the data sitting, what we're looking at right now. It's not the data sitting in the file, but it's already data in the net, sitting in the network. And of course, you could utilize the same definitions for augmenting and labeling of the data in your allotrope or whatever file. And this is exactly what the allotrope people are doing. So they're the data formats with all, they link it to the ontologies. We have the instrument data, it's linked to the ontologies, and this is how the data comes together. And it's very clear what we are talking about. So I started with this slide. Very briefly, we could talk about hours about the topics that I just touched very briefly, but you see what I showed you. There is a communication standard around LADS OPC UA. It's based on an industrial interoperability standard, which is proven, it's widespread, not in the lab, but in the rest of the world, of the industrial world. It's for the data in motion, and it's so powerful that it can provide fair data to you, and it can be linked also to the result data when via, for example, they're utilizing ontologies or taxonomies and other stuff. So this is a very powerful system, and from my point of view, a very robust and thought-through foundation how to bring digital transformation in the lab to a next level and how to enhance your data. So this was the introductory part. Questions so far? Hopefully I did not completely overflow you with strange stuff. Jochen, any questions so far or comments?
No, there are no questions as far as I can see. Yeah, no.
Okay.
Maybe later. Yeah.
Maybe later. So I simply continue. You might be curious who is behind this initiative, who did drive it. It started, and maybe you even don't know what Spectaris is. You don't have to know. It's, you know, there are associations for different industries. Like in Germany, we have the huge, of course, association for automotive industry. There are big associations for the machine builders, for the MR. This is very big, but there's also a smaller association which takes care about optics, photonics, analytical medical technologies. This is Spectaris. So this is an industry association, and in this industry associations, typically the device vendors and instrument vendors and are organized. They are members of this association, and Spectaris has 400, 500 industry members. And the ones you see down there, listed there, and hopefully you find some of the equipment vendors you utilize in your lab, like Agilent or Thermo Fisher or Arnold or whatever. They are supporters of this LADS initiative. And so they are all interested in supporting what we are doing. And of course, we made it because the VDMA is very active in standardization. So we work together with them. And of course, the foundation, it's OPC. We work together with the OPC Foundation. And the good thing about associations, if you define a standard and you make it just for Germany or for German-speaking countries, no one's interested. If you want to define a standard that really gains traction, you have to do a global approach. And the good thing is OPC Foundation is completely global. It's headquartered in the US, although there are a lot of German-speaking driving it forward, but it's headquartered in the US. And Spectaris by itself is networked to other industry associations for analytical instruments, like, for example, JIMA, Japan Analytical Instruments Manufacturers Association. And we are working very closely with them. They're highly interested. 2 weeks ago at Analytica, I met with 2 guys represented from JIMA, one from JIMA, one from Mitsubishi Chemical, and say, well, we have to bring this to Japan. So now the They're making proofs of concepts in Japan, making workshops and things like that. So it's a global effort. So this is who's behind. So it's what started here in Germany, but it's really a global thing. You see some of the vendors who are behind that. And we have also included the users. For example, Joachim Richard, he was a member of our user review committee. So we're working close with them and others from like Henkel and Bayer and whatever. Very important, we'll touch this later. You have to spread the news, you have to do a reality check what you're doing, you have to bring it in the instruments, otherwise it's just theory. So and that was new for the OPC Foundation, we organized hackathons so that we really bring the people together and that they implement the stuff, learn about the standard and implement it in their devices and in their software. And just 2 weeks from now, we will have the next hackathon. This time it will be in Duisburg. Maybe some of you know the UTA, that's the Umwelttechnik Institute. It will be there, but it will be hosted by one. Oh, he's not there, Gerstl. I think he's not shown here, but that will be the host. The last one, by the way, was at Agilent. So there's a really high interest in the industry. And by the way, there's a very nice video on YouTube of the OPC Foundation about our last hackathon, which took place at Agilent. Then it changed with peers. One of them is Analytical Foundation. I utilize this word many times in Bioforum. This is an association where, let's say, big pharma and pharma suppliers for instruments and data stuff are working together in Bioforum. And last but not least, you might recall that on the base of the OPC UA base standards, there are a lot of other standards. And what the OPC Foundation does is, in order to harmonize what's going on, that the people don't come up with different standards for the same thing, that they do a lot of harmonization. And of course, we participate in this harmonization. And if we see someone already defined something useful there, of course, we take it. And I will, you see this abbreviation CAISI on the very bottom of this tile. And at the end of my presentation, I will shortly explain to you what CAISI is, because that's another upcoming standard we are closely collaborating with, and this standard could be also of high interest for you and for your community. So this is what's behind the LADS OPC UA joint work group, and this is just to give you an impression how we try to bring it to the community, so that the device vendors, the software makers, also makers of LIMS and ELN and LES, or even also in academia, but as industry, learn about the standard, learn how to implement it. This picture was taken last October at Agilent, and you see me in front just explaining what this is about, and really explaining how here's my device to the device makers, my instrument, how can I bring this standard into the device, and what do I have to do, and what's the workflow to do so. And then in the room next to, so these were the people new to the technology. In the room next to us, there were already a lot of people hacking. You see, this is how the guys look like that make the devices you're utilizing. And there are some Agilent guys here, and these are from Gerstl. This is a nice handling thing which sits on top of an GC gas chromatograph to get the sample in, and all the other stuff. And there's some liquid handler. You see, this is people hacking, learning from each other. It's very uncommon industry that we should really competitors sit together, the developers of the competitors sit together, talk to each other, learn from each other, and it's a very great format. And 2 weeks from now, we will have our 6th LADS Hackathon. Yeah, and these are just to give you an idea, an impression who attended. This picture does not mean that you can buy it now, but those are all devices from attendees from our hackathons, where we made the instrument model for the LADS instrument model, where they implemented it. And you see, it's really tons of different devices. Here on the bottom, here on the top left, it's just a magnetic stirrer with some temperature control, or a freezer or a shaker. This, for example, is a luminescence reader. Okay, this is kind of analytical device. This is some PCR device. Down here you see an HPLC, but you also see bioreactors or balance or centrifuge, or just here that's a absorbance reader. You see, it's very broad, and it's just an excerpt of all the people working with us and interested in what we're doing and implementing it. It will take some time until it reaches the market, but some of them are already working on real products for that. Okay, I mentioned CAISI. What's that? And that might be of interest. It's an ongoing initiative, and I think it's very important to see who's behind this initiative. It's about, first of all, what's it about? Integration of analytical systems into data systems. So it's more not focused really on the instrument itself, like LADS, but just on the instrument data. And it's not next to LADS, but it's on top of LADS. So whenever you have a CAISI enabled device, it will be also LADS enabled. It's just the higher layer of abstraction where you only deal with the, even if it's a very complex modular system, how to run your experiment and how to get your data and to the analytics, to the data system. And if you look who's attending this, who's driving that, it's Agilent, it's Shimatsu, it's Thermo Fisher Scientific, and it's Waters. So, and if you put them together and think about HPLCs and GCMS system, I think it's in the lab, it's represent maybe 70% of the whole market. So this is a very powerful initiative. And we are working closely together with them. Don't going into that charter, much more important, how should it works together, fits together. Here, so LADS, that's our focus. You see, we have all those devices in the lab and with along the workflow. And then, of course, you have an instrument system like the HPLC, and I showed you many times this Agilent HPLC, and there's already one Agilent compact HPLC. You can buy it, but we have it, so we play with it, which has full LADS OPC UA support. This is where I showed you the data slides from, and of course, so LADS deals with more with the instrument view and all the data, all the way to. So here's in this model, this result was produced, like here in the, and then CAISI is concerned about if I have a very complex analyzer, modular, made up of maybe multi-vendor scenarios, how to integrate this not just to the LIMS but really to the instrument data system. So they're talking about the time series of spectra made in somewhere, so really huge amounts of data, gigabytes per second, stuff like that. So, and we're working closely together, and CAISI builds on top of LADS. So it will be another OPC UA-based companion specification, utilizing OPC UA, utilizing LADS, and building their things on top of it. So every CAISI device will automatically be a LADS device. I think that's a very cool thing, working together and having all those synergies together. And this is important for you, I think, to know, because it's what you utilize day to day in your lab. So I think through this close collaboration, we really lay a great foundation for digitalization of those stuff. Yeah, coming to the end of my presentation, I try to make a short presentation. It's, well, 40 minutes is long enough for you to listen to. And I have very different audience, talking to developers, to whatever different people. So I try to make a high-level overview and also focus on fair data and how this fits together. But the takeaway message is we need standards. Otherwise, we don't achieve the goal of digital transformation in the lab. So, and if you want to find more information, I will share this presentation. There are some links, but there are much more links that you will find on YouTube, on the web, whatever, all the way to workshops for programmers and so on. So thank you, and hopefully you got something to take away home with.